Well, one of the other things that I talked about last week was projection operators. When a carpenter builds a house, it's really important that the house be square and that it also be plumb. By square, it means all the interior angles are at 90 degrees to one another. So the walls are at 90 degrees, the ceiling is at 90 degrees to the wall, the floor is at 90 degrees to the wall, and so on. And by plumb, it means that the walls are perfectly vertical to the surface of the earth in that neighborhood. Well, sometimes after the house is built, you go back and you have to build another wall inside or a closet or something like that. And you want to make sure that the wall in this new closet is both square and plumb, which means that when you're putting the framing in for this closet, you have to take a spot on the ceiling where the top end of the post is going to be, and a spot on the floor where the bottom end of the post is going to be, and one has to be exactly over the other. So you want to pick that spot on the ceiling and project it onto the floor so that the length of the column that you're going to put between those 2 points is as short as possible. Because if that post that you're putting in is as short as possible, it means those 2 points cannot get any closer. You can't find another point on the floor that's closer to the point of the ceiling than the one that you picked. So the carpenters have a clever way to do that projection. They get a heavy weight with a point on it on the end of a long string. And they hold the string up to the ceiling and they let out enough string until the point on the heavy weight just a gnat's eyelash away from the floor. And they wait for it to stop swinging. And then they put a pencil mark on the floor. And they know that the string, heavy weight on the end, is perpendicular to the ceiling in any direction. And it's also perpendicular to the floor in any direction. So that string is the way they project from a point in the ceiling, which is in 3 space, to a point on the floor, which is in 2 space. So what we're going to do is, this is a very strangely shaped room, but let's put the origin here with my feet on it. And so one axis runs along the floor off this wall, and another axis runs off the floor this way. They're 90 degrees to one another. And the vertical axis is standing in the corner, and it's 90 degrees to either of the other 2. And then I put a directed line segment from the origin down there up to the projector. So imagine in your mind there's a line segment that runs from the origin, and it's just touching, say, one corner on the projector up there. So that's the directed line segment. I want to figure out a line on the floor that's directly below my directed line segment. So I need to construct a vector in 2 space that lies on the floor. I want to construct a linear combination of this axis and this axis so that the resulting directed line segment on the floor is just long enough so that when I drop my carpenter's clob, string of weight on from the corner of the projector down to the floor, the point on the heavy weight just points at the end of this line segment that I just constructed. So there's a way to do that arithmetically. It's projection techniques. So the question is, how do I construct a transformation matrix such that the line that I drew on the floor is as close as possible to the direct line segment that touches the corner of the projector? There are many transformations which are a mapping of the direct line segment that touches the camera down to the floor. There are many such transformations, but there's only one that's best in the sense that it minimizes the difference between the line segment that touches the corner of the projector and the line I drew on the floor. There's only one way to do that. That's a very unique thing. So the one that I told you about was that X, open paren, X transpose, close paren, inverse X transpose. That was turned out it was also an idempotent matrix, and that was a projection operator that satisfied that minimum distance criterion. So that turns out to be the projection operator that we derived from minimizing the sum of squared errors. It happens to be the least squares estimated. We are then able to go back and derive the properties of that least squares estimated. We can figure out whether or not it's unbiased. We can figure out whether or not it's efficient, whether or not it's consistent. All of that is predicated on some of these garden variety assumptions that the error terms be independently identically distributed. But suppose they're not. This is where we're headed over the course of the semester. Suppose those error terms are not independently identically distributed, as you brought up. What do we do? Well, the first job is to see whether or not, under that circumstance, least squares is still unbiased, still efficient, and still consistent. And if it's not, how do we fix it? So that's where we're headed, and why we're spending some time on linear algebra now and a bit of time on some of the distribution theory and so on and so forth, so that we get around doing these things, we can get through, we can plow through them very quickly without having to go back and recall or do things that we had forgotten about.
Could you repeat that as X open paren, X transpose, close paren?
X transpose X, so X, and now inverse outside the parentheses.
X inverse, right?
No. That's like that. X open paren, X transpose, X close paren, X transpose.
Inverse.
Oh, no, I forget now. There's a minus one. Right. Sometimes this X open paren, X transpose, X close paren, inverse, X transpose. My dissertation, one of my dissertation advisors was blind. He was going blind as an adult, totally blind. And so, you know, your dissertation advisor is supposed to read the dissertation. Well, how's he going to read my dissertation? So I had to go there and read it to him. And my dissertation was in Econometrics. So we would sit in his office and I would read to him. So for example, if I, just a simple example, suppose I had a theorem like the Gauss-Markov theorem, which shows that the square is its best linear hypothesis. So I'd read him the statement of the theorem and what the strategy of the proof was, and then I'd read him the proof. So suppose that there is another linear combination of the y's other than the one that I just gave you, then we'll call it C. We're going to retrieve the QC, and then I read through the proof, line by line. X open paren, X transpose, X close paren, inverse, X transpose, X beta. And, you know, line after line after line, and get to the next page, and all of a sudden you say, I think 3 lines ago, I think you made a mistake. And roll his chair over to the board and write something on the blackboard that wants to see where he was writing. He was right over it. So I had to listen really carefully, particularly if he had something long to say, because by the time he got done, it would just be a white smudge on the board. And sometimes I would get really, he would ask me a question, I'd get enthusiastic, and I'd go to the board and I would say, well, I think it's like this. And I'd write things out on the board and say, well, Andy, you forgot. I can't see what you've written, you've got to read it. And then describing graphs to him. I have to be very careful I do that. We have a vertical axis with this on the vertical, we have a horizontal axis with this on the horizontal. The figure has this shape to it, it's convex, and so on and so forth. So it was challenging. Any other questions?
How long would you want it for?
I don't know. But he could, in those bad old days, we didn't have PCs. And it was the early days of the teletype, being able to run the computer in real time, almost real time. So when I started college, we ran the computer from decks of cards. By the time I got to graduate school, we would sit at the teletype, compose a program line by line, sitting at the teletype. And he could tell whether or not he made a typo in typing in an instruction by the response that he heard on the teletype. Because he knew how long it was supposed to be typing in response to whatever he written. And if it went too long or too short, here was a mistake. It was pretty interesting. Anything else? Enough stories about old life.